So today we are going to discuss about free energy of ideal solution, and in the process we will understand what is ideal solution and what are the different thermodynamic parameters will be set for an ideal solution. Okay, so to start with, we know that Gibbs free energy for a single component system, or if you can tell the pure system, rather we tell that single component system. For the single component system, Gibbs free energy is a function of temperature and pressure if it is in the gaseous phase. But for metallurgical cases, we already told that we used to concern about liquid state and solid state. So that constant condensed matter condition we can ignore for pressure, or we can take pressure constant, and on the basis of that we can tell that for metallurgical process Gibbs free energy is a function of temperature. And another important thing one should know that if it is not the case, then this figure in the left hand side corner, that Gibbs free energy versus temperature, there the melting point will change as pressure will change. So if you consider the Clapeyron equation, and that is dt by dp, so melting point is going to vary if there is a change in pressure. So which system it is not going to happen? If del V equals to 0, at that case, whatever the scenario, if you change the pressure, the melting point is not going to vary. So any hypothetical case where del V is equal to 0, then only you will see, or you will get a scenario where with respect to pressure, melting point or phase transformation temperature will not going to be changed. So for metallurgical system, we used to consider only solid and liquid state. For that, we will take pressure as a constant. So now if we go from single component to binary system, then what will be our approach? That first I have to decide that if it is for any system, then Gibbs energy is a function of pressure, temperature, and new variable xb. That is the mole fraction of the B component. If there is a mixture of A and B, if you get a solution of A and B or mixture of A and B, then the composition also important factor, and composition has a role towards the variation in free energy, Gibbs free energy. So if you are taking for metallurgical system constant pressure, then the Gibbs free energy is a function of temperature, and composition is a function of T and xb. Okay, mole fraction of second element or B. And from this kind of concept, now we have to understand what is the mixing process with respect to thermodynamics. So in a single component system, what we understood, all phases have same composition, and the equilibrium simply involves pressure and temperature as a variables. But in the scenario of metallurgical system, we are only going to consider temperature as a variables. In alloys, if you take, however, the composition is not always also become variable. It's not always constant for but all the phases. So composition is also a variable. So to understand the phase changes in alloy, you need to have how the Gibbs energy of a given phase depends on the composition and as well as temperature, and if it is not metallurgical system, then pressure. Since the phase transformation, if you want to describe that with respect to spontaneity and stability of the product, then you have to understand the change in free energy, because that actually decides the progress of the process. Okay, the feasibility of the process rather. So if you take A and B of a same crystal structure in their pure states, and then it can be mixed in any proportion to make the solution. Suppose we can mix them A and B which are having same crystal structure, A and B metal, and they can be mixed with any proportion to make a solid solution with the same crystal structure. When they will make a solid solution, their crystal structure are not going to vary. That we are considering. Now, if you imagine that 1 mole of homogeneous solid solution is made by mixing of XA mole of A and XB mole of B, then the total mole of the solution will be 1. Then we can tell that mole fraction of A and plus mole fraction of B. If we sum them, then it will reach to the value 1. And XA, XB are the mole fractions. So XA plus XB now equals to 1 if XA and XB the mole fraction of A and B respectively for a particular alloy. So if again I am repeating, here we are taking a system where A and B have the same crystal structure and they are in the pure state and can be mixed so that we can get a mixture of A and B, and that can be mixed any extent, and after mixing they are also getting same crystal structure of A and B, and A and B both are same crystal structure, and after mixing the variation in crystal structure is not there. And then we are going to take that XA mole fraction of A and XB mole fraction of B, and then we'll sum up, we'll get the value of 1. So now if you want to, now we have to understand how we used to calculate single component system, then we can understand how we can calculate binary system or multiple component system. Suppose for single component system, what we have to do? Gibbs free energy calculation. If G equals to H minus Ts, and if you know the Cp value, then you can easily calculate the Gibbs free energy at particular temperature and that kind of scenario. But here simple situation is different. Here another thing is important, that is called composition, the mixing process, how mixing is occurring. So if you see, suppose G and Gb are the molar free energy of pure A and pure B at a temperature and pressure of certain temperature and certain pressure, then G1 can be most conveniently you can represent using rule of mixture that molar free energy before mixing. So before mixing there will be a G1 of the system, total A and B, make a system before mixing. What will be the scenario? That G1 equals to XA into GB plus XB into GB. That's using rule of mixture. We can easily find that. But it is a before of mixing. After mixing, the scenario will be different because the through mixing that may be certain new energy term or mixing free energy of mixing you have to consider. So now if you see here that after mixing, what will be the free energy? That G2 will be, what is the G1 minus del G mix, means some lower of that for a particular specific composition. And if you go for A and B mixing, it will become after mixing A plus B. So now what will be the del G mix? Del G mix will be del H mix minus del S mix. Now we have to find out what is del X mix and what is del H mix and how it is related to gives free energy of mixing. Okay. So again we have to understand what we are agreeing. We actually bring together X mole of pure A and XB mole of pure B and allow A and B to mix together to make a homogeneous solid solution. And A and B are having same crystal structure in their pure state, and also they can be mixed in any proportion or any extent to make a solid solution which also have same crystal structure. So this is the scenario. Now, and in the process, we just before mixing, what we got, that G1 equals to XA into GB, XA into GA plus XB into GB using rule of mixture. And after mixing, what we are going to get new Gibbs free energy, which is G1 minus del G mix. Now, what is G1? G1 equals to H1 minus TH1 if you think like that, and G2 is equal to H2 minus TS2. So now if you want to get the del H of mixing, then what will happen? H2 minus H1, and if you go for understanding del S of mixing, then S2 minus S1. Now for as a whole you can write del G mix equal to del H mix minus T del S mix. And del H mix is a heat absorbed or repelled during the step. It depends upon the A atom is repelling the B atom or attracting B atom, or it is neither repelling or neither attracting. These three cases, three scenario can happen. Based on that, the del H mix will have different values. It is the heat absorbed or evolved during this kind of scenario. So the heat of solution, you can tell also heat of solution, and ignoring volume change, if you during the process, it depends only the different internal difference in the internal energy. So if you ignore the volume change, then it actually represents difference in the internal energy. And del S mix is the difference in entropy between mixed condition and unmixed condition. Means if you talk about del S mix, it is actually the difference in entropy between the mixed and unmixed state. Now, if you go for ideal solution, del H mix equals to 0. What does mean? The del H mix equals to 0 means that the A atom and B atom, if it is a binary solution, what we consider for today's discussion, and that A is neither attracting B and is not repulsing B, because there is no repulsion force and attraction force between A and B. They are neutral. They are very neutral to each other. There is no attractive force between A and B, no repulsive force. So in this scenario, if such a things are happen, then we can represent the solution is the ideal solution, and then we can tell that for that solution del H mix is 0. So in which case the resultant solution is ideal, and the free energy chain on the mixing is only due to the change in entropy. Because if you go for previous slide and if you understand del H mix, the del G mix equals to del H mix minus T del S mix. If del H mix equals to 0 for ideal solution, then del H mix is strongly depend only on the minus T del S, this term. So this depends on the change in entropy, not change in the enthalpy. So if you go for statistical thermodynamics, now till now what we understood about the entropy, it's related. We relate towards the vibration. Means we consider thermal entropy. But now we have to understand what is configurational entropy or entropy due to mixing. So entropy, change in entropy due to mixing, or related to a configurational entropy. When you are talking about configurational entropy, you are actually talking about arranging different particles at different manner. How many different manner you can arrange the particle? How many permutation and combination process you can apply and arrange a different particles in different manner? That actually talks about configurational entropy. And if you want to understand such kind of concept, then you have to go for statistical thermodynamics application, and then you have to find out quantitatively the randomness related to the Boltzmann's equation. That is a one equation is proposed by Boltzmann equation. Here S equals to K kappa ln omega, where K is the Boltzmann's constant and omega is the measure of randomness. So if you go for configurational omega, that arrangement, different arrangement, possible arrangement, then you can go using the permutation combination concept of mathematics, Na plus Nb factorial of that by Na individual factorial and Nb individual factorial. And in this equation, Na is the number of A atoms and Nb is the number of B atoms. So you have to understand first Now we are introducing a new concept that is related to the configurational entropy. So for that we have to understand the disorderedness or randomness, and degree of randomness is related to entropy. It can come from thermal component, can come from thermal entropy, can be configurational. In the case of thermal entropy, omega is the number of ways in which the internal energy of the solid can be divided among the atoms. So if you are talking about, let's think about K ln omega. Now we have to understand what is omega, what omega represents. If it is thermal entropy, then omega actually the number of ways by which a thermal energy of solid can be distributed or divided among the atoms. That is the total number of ways in which vibration can be set up in the solid. So omega will represent, in case of thermal entropy, is the number of possibilities, number of ways in which the thermal energy of the solid can be distributed, can be divided among the available atoms, and that is the total number of ways in which vibration can be set up if you are taking in the solid. So setting up vibration by distributing the thermal energy among the atoms. It is the possible or number of ways, that is ways that actually represented by omega if you are considering thermal entropy. That gives extra entropy, that you can tell entropy of configurational entropy, for which omega is the number of distinguishable ways of arranging the atom in the solution. Now another that actually happen in case of solution, additional randomness can come, because there are two different type of atom or if it is a multi-component system, more than two different types of atoms will be there. So their arrangement also, interchanging their individual position, their arrangement also important, and that gives, in case of solution, not single component system, the additional randomness exists. Why exists? Because this additional randomness comes from the different way in which atom can be arranged. So in solution, the additional randomness is coming due to the different ways in which the atoms can be arranged. This gives additional entropy, extra entropy, S configuration, for which omega is the number of distinguishable ways of arranging the atoms in the solution. If there is no volume change or heat change during the mixing, then what will happen? Then first you have to understand, if there is no volume change or heat change during the mixing, then the only contribution to del S mix is the change in configuration entropy. There is no volume change, there is no thermal entropy concept, is not there, no heat change. That time the mixing, during the mixing, the only contribution will be the del S mix, is the change in configurational entropy. So before mixing, the A and B atoms are held separately in the system, and there is only the distinguishable way which the atoms can be arranged. You can get the number from that S ln omega, and if S is K L omega equals to 0, so del S mix is directly going to the change in different position configurational entropy. So now you can assume that A and B mix to form a substitutional solid solution, and then all configuration of A and B atoms are equally probable. If you go for probability theory, the number of distinguishable ways of arranging the atoms on the atom sites, different atom site, will be like that. W configuration, omega configuration equals to total number of sites available, factorial of that, Na plus Nb, and by individual different atoms, Na factorial and Nb factorial. Whereas Na is the number of A atoms and Nb is the number of B atoms. Now, already I told that here we are dealing with a 1 mole of solution, and that is N atoms. It's 1 mole of solution actually, that is N atoms, that is the Avogadro number atoms we are dealing with. So total number of for 1 mole atoms, 1 mole solution we are talking about. So the total number of atoms will be Avogadro number. N is Avogadro number. Now what will be the Nb? The mole fraction into Avogadro number, and Nb will Na equal to Xa into N, and Nb will to equals to Xb into N. And we have to find out the scenario. First we have to test scenario where we are using 1 mole of solution and we are talking about ideal solution. And since we are talking about 1 mole of solution, that is our number of atoms we are having is the Avogadro number. That is, we are telling that here for this discussion, capital N. So Na will be Xa into capital N and Nb will be Xb into capital N. Now we have to find out how to use certain mathematical expression or certain approximation. Stirling approximation, that does mean that if you are going for ln n factorial, it equals to n ln minus n. And also you can use the relationship Avogadro number multiplied by Boltzmann constant equals to R, that is universal gas constant. So if you use both these two relation, then we will easily get del S mix equal to minus R in the bracket. If you multiply Xa into ln Xa plus Xb into ln Xb, this is actually, you can tell, entropy of mixing. It's coming from configurational entropy, and it is the entropy of mixing of two different type of atoms, A and B. Okay, and we are discussing all the process through 1 mole of solution. Now del S mix we understood, and based on that we have to find out what will be the del G mix. So if you talk about del S mix, now del S mix will be in A to B. If you see this curve will like that, if you see the expression of del S mix, now if you multiply with minus t, then what will happen? The nature of the curve will be same, only scale will be varied because based on the value of t, but the nature of the curve will be same and it will be in the negative part. And if you see previously that we only got a scenario where the before mixing total free energy we have plotted, that is a linear line, and we used a linear mixer volume of mixer rule. So the rule of mixer when we are used, then only get to G1, but due to mixing process our Gibbs free energy will be G1 minus del G mix. Now if you check here this we have to subtract by del G mix to get the actual Gibbs free energy with respect to composition. This is the Gibbs free energy versus composition diagram. Okay, so what will be the del G mix now is equal to RT ln Xa plus Xb ln Xb. So you can now see that Xa and Xb are less than unity. So del S mix should be positive because Xa and Xb are less than unity, and there is an increase in entropy of mixing. So if you check previous slide, here always del mix is a positive. Why is it so? because XA and XB less than unity, and you are considering what you are considering? You are considering del S mix equal to minus R into in the bracket XA ln XA plus XB ln XB. So it shows that now if you going to plot with del S mix with respect to XA or composition, then it is always going to be positive. And there is an increasing entropy on mixing as expected. Now, because when you are doing mixing, del S always increase. Del S mix always increase. So now you are going to get the free energy of mixing. What is that? That RT in the multiplication in the bracket XA ln XA XB ln XB. So in the previous some figures or in the figures in the slide also you can see that actual free energy of the solution, it depends upon the GA GB as well as the del G of free mixing. So the temperature, if the temperature is increasing, GA and GB decrease and the free energy curve assumes greater curvature. If your temperature is increases, you are going to get free energy curve having greater curvature. And the decrease in GA and GB due to thermal entropy, both components. So why it is decreasing? Due to the thermal entropy component. So now we also think that free energy composition diagram, what we are seeing in this slide, it's a basically schematic, not as per proper scale, but you can get a understanding or concept seeing the molar free energy. So what is molar free energy versus composition diagram? What is molar free energy? Free energy per mole of a solution. That is called molar free energy. And here whatever you are seeing is for the ideal solution. It's ideal solution means del H mix equals to 0, means that A atom and B atom does not repel each other, does not attract each other. It's just independently they can distribute. Okay, and they are equal likely to take a position of available atomic site in the mixed system. So now today what we learn that if there is a system where del V is 0 and if also it is a hypothetical system, then a solid becomes a liquid where there is no change in the volume. In such case, delta V is equal to 0, and in this case we can tell that if delta V is 0, dt by dp also equals to 0, and that means if delta V is you get the 0, you can say that melting point never going to change with a pressure. That is one takeaway of today's class. And another important thing, that we should understand how del S mix is related to configurational entropy, and it is always positive if you are getting the different composition variation, and T multiply by T del X and minus sign of T, it will be negative, and it actually only contributes towards del H mix, because in case of ideal solution it only contributes because in ideal solution del H mix equals to 0. So this is two important understanding of today class. Thank you. Today class is over.